This is a production of the Chemical Education Material Study.
Chemical reactions between gases have so many practical applications that we take them for granted. Yet such reactions provide one of the first bases for postulating the atomic theory. Understanding such reactions led to a direct way to measure molecular weights. How this was first recognized is an interesting detective story. Let's hear how it goes.
We think of gases as collections of particles to explain their similar pressure-volume behavior. But in other properties, gases differ. An obvious difference is color. This gas called nitrogen dioxide is reddish-brown. Chlorine is pale yellow-green. But most gases are colorless. But gases differ in much more important ways. For example, let's investigate solubility in water. These three test tubes have been filled with three of the gases. The first contains nitrogen dioxide. When the test tube is opened underwater, the water level rises, showing that the gas dissolves. The next test tube contains oxygen. This time the level does rise. Oxygen has low solubility in water. The third test tube contains hydrogen chloride. Hydrogen chloride dissolves readily and rapidly. On the basis of such tests, we have grouped the gases according to their solubilities. A test commonly used to identify oxygen is the ignition of a glowing splint. Perhaps we can use this familiar test as a basis for further segregation of these gases. Let's try it first with hydrogen chloride. The splint does not burst into flame. Ammonia behaves the same way. With hydrogen, a small explosion. Let's try nitric oxide. Watch this. As air enters the bottle, the color changes to a reddish brown, like the color of nitrogen dioxide. We still have not distinguished these two gases, ammonia and hydrogen chloride. The dye, bromcresol, will help us. These pieces of paper have been soaked in an alcohol solution of the dye. Let's see what happens when the dye comes in contact with ammonia. The dye color changes dramatically. When the dye goes into hydrogen chloride, the color change is reversed. Thus, bromcresol distinguishes these two gases. What color would the dye be if the gases are mixed? Let's try it. Oh, we can't answer that. When these gases are mixed, we get a white smoke. So we can distinguish these gases qualitatively. We can learn much more about molecules by making quantitative studies. A quantitative study is concerned with the question, how much? For example, how much hydrogen chloride gas will combine with a fixed volume of ammonia gas to form this white solid? This apparatus is suited to such a measurement. This chamber has been filled with ammonia gas from this tank. It's connected through this tube to a similar chamber on the right. This one is now filled with mercury. When we open this stopcock, we can fill the right chamber with the second gas, hydrogen chloride. We have more than we need. This leveling bulb controls the pressure in the right-hand chamber. A similar bulb controls the pressure in the left-hand chamber. Now let's remove some of this hydrogen chloride. We disconnect the tube and allow some of the hydrogen chloride to escape. With the pressure adjusted to 1 atmosphere, the reading is 0. Now, let's raise the pressure in the right chamber by lifting this leveling bulb. This will force some of the hydrogen chloride into the left chamber when this stopcock is opened. Again, we see the white smoke as the hydrogen chloride combines with the ammonia. The mercury levels rise as the gases are consumed. Now the pressures on both sides have been adjusted to 1 atmosphere with the leveling bulbs. The center tube is connected to the left chamber to show more clearly how much ammonia has been consumed. The reading in the left chamber is 21 milliliters. In the right chamber, the reading is 22 milliliters. Now we have quantitative information about the way these two gases combine. Hydrogen chloride (22 milliliters plus or minus 1), and ammonia (21 milliliters plus or minus 1). The ratio of these two volumes is 1.05, and the figure is not significant. Now let's repeat that measurement. The apparatus has been refilled and the levels of the two gases again adjusted to 0. This time, let's wait until all of the ammonia is consumed. After adjusting the leveling bulb on the right, we can see how much hydrogen chloride was needed. This time, 30 milliliters of hydrogen chloride combined with 30 milliliters of ammonia. The ratio of these volumes is 1.0. Now you can see that these results are in agreement within experimental uncertainty. The volume ratio is, on the average, 1.0. We have found that 1 milliliter of hydrogen chloride gas combines with just 1 milliliter of ammonia. Think what a simple result this is. It could lead us to wonder whether other gases combine in the same simple volume ratio. This apparatus permits us to mix hydrogen and oxygen and study quantitatively how these gases combine. When we loosen this clamp, hydrogen enters the tube. The scale reading is 10.1. Let's record the data. Hydrogen, the scale reading was 10.1. We'll add an equal volume of oxygen. The scale reading is 20.1. For oxygen, The final reading was 20.1, the initial reading 10.1, the difference 10.0. Now we can ignite the mixture by means of a spark. This is a high voltage coil, not unlike that used in an automobile to generate the spark. By this wire at the top, we can spark the mixture. The scale reading is 4.9. After that spectacular reaction, some gas remains. Water from the beaker has risen in the tube, taking the place of gases consumed during the explosion. The gas that remains could be hydrogen, oxygen, or some other gas. Perhaps a splint test will give us a clue. You recall that hydrogen caused a small explosion, whereas oxygen caused the splint to burst into flame. Ah, the gas behaves like oxygen. Apparently, only a part of them was consumed. The volume ratio can now be calculated. Presumably, all of the hydrogen was used. Whereas the difference between 10.0 and 4.9, 5.1, tells how much oxygen was used up. The volume ratio is 10.1 over 5.1, 1.98, or 2.0. Let's add this number to our summary. The volume ratios are not the same, but they're both simple. These simple integer volume ratios, 1.0 and 2.0, lead us to wonder whether all gases combine in simple whole number volume ratios. Let's try another example. Remember that nitric oxide combined with air. Let's try that one. These two cylinders have been filled, the right one with nitric oxide, the center one with oxygen, one of the constituents of air. First, we remove the screw clamps. Blowing into this tube causes water to enter the oxygen chamber. This forces oxygen over into the nitric oxide chamber. The color of nitrogen dioxide appears. We see that oxygen is the constituent of air that combines with nitric oxide. The water continues to enter the oxygen cylinder as long as oxygen remains. Then, when the oxygen is expended, water begins to transfer into the nitric oxide chamber. We see the color of nitrogen dioxide is decreasing. Remember, nitrogen dioxide dissolves in water. As the nitrogen dioxide color disappears, the water transfer ceases. Now the color is gone, and we see that the water level is slightly above the halfway mark. When we open the cylinder to the atmosphere, no color forms. That indicates that no nitric oxide remains. The splint test shows that the residual gas behaves like oxygen. So we see that nitric oxide combines with oxygen and one cylinder of nitric oxide combines with just 0.50 cylinders of oxygen. The volume ratio is 2.0. Once again, we have a simple 2-to-1 volume ratio. There's one more example we can investigate with the gases we have here. Hydrogen combines explosively with chlorine as well as oxygen. We have set up an apparatus for this experiment. The combination of these gases is unpredictable, so we have an explosion shield in place. Hydrogen has been placed in the tube. The reading is 10.0. Now we're ready to add chlorine. We can spark the mixture as we did earlier. The water rose, almost filling the tube. The combination of hydrogen and chlorine gives a substance that dissolves in water. This is one of the tests that show that hydrogen chloride is produced. But our interest lies in the volume ratio. We mixed equal volumes of hydrogen and chlorine. There was no excess of either. The volume ratio is 1.0. In every example we studied, the volumes of two gases that combine are in a simple integer ratio. These ratios represent irregularity. Now let's seek explanations. First, different gases have different properties. The molecules of one gas must differ somehow from the molecules of another gas. Next, we discovered there's a simple integer relationship between the volumes of two gases that combine. A simple explanation of such relationships was first proposed a century and a half ago by an Italian scientist, Amedeo Avogadro. If you wish to discuss at this time what these new facts add to our particle model of a gas, the projector may be turned off now. Then, later, you can compare your ideas with those of Avogadro. How should we modify our particle model of a gas to explain these simple volume ratios? One volume of ammonia combines with one volume of hydrogen chloride. One volume of oxygen combines with two volumes of hydrogen. We picture these gases as collections of particles. Chemists call these particles molecules. Hydrogen chloride consists of particles or molecules as well. But these molecules differ somehow from those of ammonia. The chemical properties of these two gases are different. Now, the simplest assumption we can make is that one molecule of ammonia combines with one molecule of hydrogen chloride. The process continues, forming the white solid, until all of the ammonia is gone. Then, experiment shows us that all of the hydrogen chloride is gone. We have represented too many molecules of hydrogen chloride. This assumption leads us to conclude, then, that equal volumes contain equal numbers of molecules. This is just an hypothesis, of course. If one molecule of ammonia combines with one molecule of hydrogen chloride, then equal volumes contain equal numbers of molecules. Let's see whether this hypothesis is consistent with the other volume ratios. For example, can we explain a volume ratio of 2 with this assumption? We have set up the oxygen-hydrogen case with this same assumption, that equal volumes contain equal numbers of molecules. 2 volumes of hydrogen combine with 1 volume of oxygen. This leads us to propose that 2 molecules of hydrogen combine with 1 molecule of oxygen. The result is in agreement with experiment. 1 volume of oxygen combines with 2 volumes of hydrogen. our hypothesis is still useful. This is the explanation that was proposed so long ago by Amedeo Avogadro. Equal volumes of two gases at the same temperature and pressure contain equal numbers of molecules. This hypothesis has stood the test of time. Still today, chemists make frequent use of Avogadro's hypothesis. Equal volumes of two gases at the same temperature and pressure contain equal numbers of molecules.
Avogadro first made this proposal in 1811. Today, this hypothesis furnishes a cornerstone of our understanding of the reactions of gases. One wonders if Avogadro realized how far his ideas would go.